Hello, we are Team 5, and our project is titled McToT, Monte Carlo Enhanced Tree of Thought. Currently, LLMs have limited reasoning abilities, and they struggle with multi-step reasoning and dynamic branching problems. Current reasoning approaches rely on explicitly defined thought paradigms such as chain of thought and tree of thought. The best performing thought paradigm we have, McToT, or everything on thought, only uses LLM in auxiliary capacity and still relies on programmatically defined state and action spaces specific to the problem. Our project attempts to build on the TOT paradigm to develop a general LLM-based problem-solving framework. We use the problem of solving Sudoku puzzles as a testbed as it requires multi-step planning across many possible actions, just like many real-world problems do. In the tree of thought framework, the root node represents the problem, and the LLM proposes next steps to explore the solution space. If an invalid node is reached, it backtracks to a previous state and explores other options, repeating until a terminal state or solution is reached. This process, a depth-first search guided by the LLM, can be resource-intensive due to exploring invalid paths unnecessarily. Our solution enhances TOT by adding a value model to evaluate the likelihood of each state to reach a terminal state. Like the example we are showing, we ask the value model what's the state score for each node and then pick the best node to explore until we find the terminal node, which can reduce redundant exploration and find solutions more efficiently. So how do we implement it? Concretely, the input puzzle is provided as a string, which is given to the LLM to propose the possible actions we can take from that state. These possible actions represent what the next steps in solving the puzzle might look like. Once the possible actions are generated, they are evaluated by a value model to determine the prospect of reaching a correct solution from that action. We then execute the most promising action to obtain a new state. The overall framework repeats this process until a terminal state is reached. The framework then decides whether the terminal state is a correct final answer or backtracks if it's incorrect. An accurate value model capable of estimating the expected future reward of each state is crucial to our approach. We use Monte Carlo tree search, or MCTS, during training to estimate the expected future reward of each state. MCTS is widely used in puzzle solving with much success, and we further improve its generalizability, leveraging the flexibility of LLMs by asking an LLM to propose and execute actions and evaluate outcomes, as opposed to defining them explicitly. Here are some examples of state values estimated by MCTS. As you can see in the highlighted puzzle, there are already 2 2s in the second column, so no further action from this state could possibly lead to a correctly solved puzzle. And the MCTS thus correctly estimates the value for that state to be -1. But for the puzzle highlighted in green, all but 2 cells have been filled, and there are currently no rule violations. And all that the LLM needs to do to solve it correctly is to figure out the remaining 2 numbers, which is relatively easy. So the MCTS correctly estimates a value of +1 for that state to denote that it's likely that we'll be able to solve the puzzle correctly from there. After training a value model on these simulated data, we evaluate our approach on the same test dataset as originally used by TOT, 10 3x3 Sudokus as shown on the right. This is our evaluation result. The result shows that by using a value model, we are able to improve the accuracy, the number of LLM invocations, the total token count, and the average problem-solving time meaningfully. This is because with a value model, we can prioritize actions most likely to lead to correct solutions. In conclusion, this framework combines an LLM, a value model, and the tree of thought paradigm to solve puzzles and make decisions efficiently. It generates possible actions, evaluates them with a value model trained on MCTS-generated scores, and selects the best action at each step. This process continues until a correct answer is reached or all actions have been explored, offering a systematic and effective approach to problem solving without sacrificing generalizability and autonomy.